Good morning, everyone. This is the beginning of the fourth module, where we'll take 6 hours to look at systematic problem solving and applications. Before I go to solving the problem, I'm going to take time today to briefly tell about certain common equipment, devices, or machines where thermodynamics is the starting point of the understanding. When we put these things together in a sequence, we make cycles. So today we will spend time looking at the common thermodynamic devices, look at the processes that happen in them, and see what are the major assumptions and the reasons why we make those assumptions in solving the problems. So we start by looking at a list of some of the common equipment which you will come across in problems. I've listed here a bunch of them. We will begin with looking at positive displacement devices. So these are devices that either compress or pump, or the opposite thing, they take high pressure, high energy fluid and deliver work. Positive displacement is the reason for giving this name, and when we look at the construction of these, we will know that how these are different from other types of devices. The next we will look at is a heat exchanger. This is a very common device, and basically here hot fluid gives energy to a cold fluid. So the temperature of the hot fluid decreases, the temperature of the cold fluid increases. The next category of equipment we'll look at is what I listed here as compressors, fans, and blowers. These are centrifugal devices which either increase the pressure of a gas or a fluid or a liquid, or they don't increase the pressure too much but deliver large flow rates. The fourth type of equipment we will look at is what is known popularly as a pump. And in particular, in this thing, we will look at centrifugal pumps. Now, just to remind you that the most commonly used engineering machine all over the world is the electric motor. And the second most common machine in use is the centrifugal pump. So that's how common these devices are. And we will look at that. Then we'll look at a turbine. So this is a device in which we put either steam or gas and expand it and get work out of it. That work can be used either for propulsion or for generating electricity. Then we'll look at what is known as a valve in general, and in particular we'll look at a type of valve which is called the expansion valve, in which we expand the fluid without much change in kinetic or potential energy. We'll look at that. This is what actually happens when in a pipe you put a restriction, it dissipates energy, there's a pressure drop, but the velocity doesn't increase too much. Nozzles and diffusers are devices that have a specific purpose, that in the case of nozzle, we want to accelerate the fluid to achieve a particular purpose, whatever that is. And the diffuser, we want to decelerate the fluid. So we'll see where these two get used. And then we will look at something which connects things in a system. So it's a refrigeration system or a power plant system or anything like that. So we pick up some equipment from these and connect them to each other, and we produce what is known as the cycle. So we look at how do we do analysis of pipes, tubes, or duct in thermodynamics. You will also come across these and many of these in your fluid mechanics courses also. So they are not very much different, but in the fundamental sense, all of these devices have to obey the laws of thermodynamics. There is no exception to this. We will also add two more things to it. One is what I call is a mixing process. where we in this case, we take the same fluid at two different states, put it together, mix it to produce something else. And the last thing we'll look at is filling, or you may call evacuation, of a tank or a reservoir or any such device. So what we are doing is, in this case, putting fluid into a chamber or drawing fluid out of it and not being able to maintain the state inside. So that's why it will be filling or evacuation. So with this, we largely cover all the equipment that are there from which we can create thermodynamic systems. Or if we get a thermodynamic system, we should be able to identify which of the equipment is in which category. And today we will see what are the salient features of that. And tomorrow I'll show you some more pictures of these devices, what they look like in the real world. So let's begin it by first looking at a simple example. And the one that I've chosen here is a refrigeration system. So a refrigerator or an air conditioner, whether it is the domestic one, which is a small little device, or could be a big one, which is like a centralized air conditioning system where the equipment is big. They all have four basic equipment. One is the compressor. And as the name suggests, it takes in low pressure vapor and produces high pressure vapor. High pressure, in the process the temperature also goes up. The second device we have is the condenser, where we condense vapor to a saturated liquid or slightly a subcooled liquid. The third device is the expansion valve, where the saturated or subcooled liquid goes in, throttle, it changes phase and the temperature drops. And it is this drop in temperature and the cold fluid that we get, which we send into the evaporator. And the name suggests, what we had was a mixture at low temperature of vapor and liquid. This takes heat and the liquid evaporates to become vapor. In the process, it draws heat out from the surroundings where this is and gets heated up. So we have four major equipment whose thermodynamics we know how we are going to analyze. And to complete the cycle, we say that this will be connected to this in this manner. The outlet of the condenser will be connected into the expansion valve. The outlet of the expansion valve will lead to the evaporator, and from the evaporator we send it back to the compressor. So we have four equipment, and what these are tubes or pipes. And the diameter, the length, the material, their design requirements, they could be different in the four sections. The fact is that we assume that we have also connected them with pipes from the outlet of this to the inlet of this, and like that, there are four pipes. And the next thing we do is, we say, look, I want to do the analysis of this. So I have four equipment and then four pipes. So there are 8 components that complete this system. And we can say that the flow in this is like that. So we can even put a arrow like that and say that, well, the material flows like this. And to that, we can, inside this, we can also add what is the material that is in there. So you can put there, say, R122 or 134A, and it tells you what is the working substance that is flowing through this. And we'll now go through the individual items and see what is it, how can I do the analysis of this? And then we will say that how do I do the analysis of the tubes or the pipes? And finally, what is it that I can put together and say, look, I want to design something to do so much cooling, or I have a system and I want to make measurements and understand how well it is performed. Either of those could be our objectives. So one is a performance objective, the other is a design objective. So one of the things we do in the beginning here is that we say that in the pipes and the tubes, we assume that there is very little pressure drop or heat transfer. That means the state of the fluid coming out here is the same as the state going in there. So in this pipe, the state of the fluid is not changing. So we can say that this entire length, we can denote it by state 1. The same assumption tells that we assume that in this pipe, there is no pressure drop, no heat transfer, there is just an ideal flow, and so there is no pressure drop from the outlet of the condenser to the inlet of the expansion valve, no matter how long this pipe may be. And all of this is the same state, and this we will denote as 2. The same thing we do in this pipe. We say that from here to here there is no change in properties, and so this we will call as state 3. And the last one is from there to there, and this we will say is state 4. So we have 4 states to work with, and in either case, whether it's design of a problem or analysis of an existing system, we essentially are looking at information about these 4 states from which we can calculate the performance of these 4 devices based on what thermodynamic relations happen in the processes. This is the starting point of all things where there is a cycle. And there are many things where even if it is not a thermodynamic cycle in the sense that we have learned here, even if it is the flow system, we would begin by looking at an analysis like this one. In such cases, what we can also do is, we can say that I want to have one picture which gives me a complete information about everything that is happening here. And so what we can do is, we say that at this point, I'll put a line and put this thing here, and say that here I will write the pressure P, the temperature T, and here I can write the mass flow rate and the specific enthalpy. In case there is a wet state, we make a small change. Because pressure and temperature are the same, we can give either pressure or temperature, and that we'll have to mention the dry instruction there. So what we have basically done by putting this type of an information here, and these could actually be the numbers, the real numbers that are there. We specify what the units are, and we can say that, okay, this is in kilopascal, the mass flow rate is in kg per second, the temperature is degrees Celsius, and specific enthalpy is in kilojoules per kg. So each state gets completely defined on this diagram. And if you look up such diagrams from any manufacturer, say of a power plant, they will write one more very important piece of information which says that, okay, for this substance, I am telling you that these are the properties, but how did I get these? And so they will always write what is the source of the properties. And as I put out the solutions for the third module, what happens is there are many places from which one can get properties of any working substance, including many online websites. And if you use one or the other, you will see slight differences from one source to the other source. In some cases, the differences will be very small. In some cases, the differences could be large, in large part because the reference state at which they have taken S equal to 0 or H equal to 0, that is at different temperatures. So the absolute values could change in that case. But what happens is that as long as we are consistent in using the same property source, we don't have a problem. Because in almost all these cases, wherever we are looking at changes in properties across a device, we invariably come across difference of two properties, H1 minus H2 or S1 minus S2, and that difference is largely independent of the source from where these properties are taken. So if the designer of the system used a particular source and we are checking that calculation based on properties from some other source, this could be a book or a table or a website, we could find some differences in the values that we get over here, but largely the differences will be small, but in the end there will be some deviation from what has been given because of the source, and the second deviation will also come because of round off. The property tables that you would have come across, in some cases they are up to 4 places of decimal, some 5 places of decimal, in some cases only 2 places of decimal. And that is given because it means that those are the significant places over which the designer of this property is confident that there is no error in that. The next place of decimal is in doubt. So if you are doing calculations and giving answers, we must not add too many more decimal places after that, because your source did not have that much accuracy to begin with. So please keep that in mind when you report answers to a calculation. The calculator may give you 8, 9 decimal places, but in the end, the goodness of your property is how good your final result will be. You cannot do anything more than that. Please keep that in mind. So the round off is an important feature. So there will be cases where we have done round off in the solutions also, somewhere 1 decimal place, somewhere 2 decimal place, and you could find that there could be a small difference between what you get and what is there in the solution. In case there are doubts, please do post it on the forum. I will cross-check and clear those doubts. But the important part is the source of the properties in the round off will cause differences in numerical answers. But the formulation of the equations, if that is correct, most of the things we have done right, the next step can easily be checked out. Okay, so this is how we will put together things for a cycle. But there are many cases where we will not be studying a cycle. In the application, we are only going to look at one component. So in that case, we will just take one portion of this, only this part, and give the inlet outlet states here and there, and do all the analysis from that point. So the same process we will follow for a single process. A device like this is a flow system, and a picture like this is called a schematic diagram or flow diagram, which I hope you have learned in one of your engineering drawing courses. Almost every system design begins with this. It could be something like the fuel system of a car, but the first picture that the designer will make is, well, what are the equipment that I'm going to put, how I'm going to connect them, and decide what are the equipment that are there, and then we go about doing the engineering of the device. The same thing in a POS plant or a cogeneration plant or a combined cycle power plant. Same thing in the beginning. This is the beginning thing to design that process. Once we have done the thermodynamics of this, we get a lot of information which tells you what should be the mechanical design out of all of this. For instance, this tube, if we know what are the properties here, what is the flow rate, then we can decide that what should be the diameter, what should be the thickness, so that it can withstand that pressure, and what should be the design pressure based on the thermodynamic pressure that has been told to us from this side. The evaporator, for instance, we will know that we need to go from this state to this state and so much mass flow rate is there. When we can calculate and see how many tubes are required, how many fins are to be put, what is the physical shape and size of it, what should be the pressure for which the tube should be designed so they don't rupture. All those designs follow this fundamental information. So in the design of all of this, this particular type of a system is hugely important, and it's important we get it right. Okay, so this is the idea of a schematic or a flow diagram, and now we will start looking at individual equipment. The first thing that I will look at is what I've listed here as positive displacement devices. And by positive displacement, we mean that once you have a substance taken inside a device, no matter what the outlet condition, when you operate it, it will push it out. There is no way that it will just stay inside. So the way we can do it in the real world is the most classical thing that you have come across, which is the cylinder piston arrangement. For instance, if there is an inlet and outlet on this, and this is, say, handling air or, say, a liquid, then irrespective, once the fluid is inside this, the piston will compress it, and the moment the pressure inside is more than the pressure outside, across between which there is a valve, it will push it out no matter how much pressure is there. So in the worst case, if the outlet has been completely closed, the piston will still try to push it out. If that doesn't go out, the pressure will keep increasing, then something in this will break. That's the critical thing of positive displacement devices. The other ways to achieve positive displacement is through a gear pump or a gear type of a compressor, a screw device. You have two screws in mesh, one is powered, the other is idling, and as the fluid moves along the length of the screw, the volume that it occupies in which it was trapped keeps decreasing until it reaches the outlet and is sent out. That's a screw compressor or a screw pump. And the third one is a scroll type of a device. Scroll is that you have two plates, just something like this, which are sitting with one another, and one of them is rotating, the other is stationary, and in the process, the fluid gets trapped, gets compressed, and pushed out. So these are devices in which there is a negative work, that means they are work consuming devices. The other big example of positive work output is the internal combustion engine, in which the same thing happens, but there is a net work output. There could be 2 strokes or 4 strokes, that doesn't matter. One of these strokes produces the power, the other 3 or other stroke does something else to keep the machine going. So the way we analyze this, and in this course we will assume that there is no fuel coming in, is that we say that first, in all these cases I will define my system boundary, and the system boundary in this case is our system over there. And we know that as the piston goes up and down, the shape and size of this could change, and if there is an outlet, things could even be going out, or there is an inlet, as it comes down, it could be taking material in. If these are open, this becomes an open system. Otherwise, largely we will look at closed systems. Once we define that is a closed system, the next thing we have got to see is what is the working substance in this. And so we write down that the working system could be this gas, or it could be a wet saturated state, or it could be a liquid, and we write down the name of that. Nitrogen, oxygen, or butane, whatever it may be. So we know that in subsequent solving, when I need to get properties, which material is there for which I should get standard data. Then it tells us that once you have decided whether it's a closed system or an open system, in this case we are looking at, say, a closed system, we know what are the equations we need to use, and we write those equations. And it's important that when we write these equations, we make no assumptions at this point, but we write the full equation. In this case, of course, mass is constant, and we know that for a closed system, we have to write the equation that Q12 is equal to W12 plus E2 minus E1, which is the first law of thermodynamics. So conservation of mass, conservation of energy, we write this. We could also write the second law equation and say, what can I say about the entropy for this system? In many calculations, this may not be required, but if we say that this is an isentropic process, then we can write down that entropy change in this is 0. Otherwise, this will be an increase in entropy. So after writing the equations, the next thing we need to do is, what are the assumptions that I can reasonably make in making this analysis? It requires a little bit of a physical feel for the machine and the problem and the real world thing. That's the best way to say, well, what is a good assumption, what is not such a good assumption. When we look at this, at some things we can make clearly that this volume is small enough that the center of gravity of the system does not change too much with during this process. It may be a few millimeters, few centimeters, but not like 100 meters or something like that. Then we would have to worry about potential energy changes. So we can say that delta PE is 0 and the system itself is not moving, it is stationary. So we can say that delta T is 0. So this is something we can put here. And the moment we do that, we know that life becomes a little easier. You can write E2 minus E1 as U2 minus U1. And we now got the equation that we need to solve. If we know what is the heat transfer, if that has been known, if we know that it's an adiabatic system, we know that Q12 is equal to 0. In that case, this is the relation that we are left with. Then we say, well, how can I calculate work for this? And say, well, there is work being done at the piston boundary when there is a force there, and this is doing the work against what the piston does. The piston could be having forces coming on the connecting rod, or also frictional forces between the piston rings and the liner. All of that will be equal to the work done by the gas on the piston, or the opposite sense, work done by the piston on the gas. That we now know can be done as integral PdV, going from whatever the initial state was to the final state. And we need to have some relation between pressure and volume to know this. The common thing we came across was that we could say that this is some sort of a polytropic process, PV to the power n is equal to constant. This could be for a gas or even a saturated substance. And then we can say, well, how do I get the properties? And this is where we get now into two lines of action. If this whole thing was only a gas, and that's something we need to say, the working substance property. Say we have a gas, and can I assume this to be an ideal gas? We are not necessarily going to keep on calculating PR and TR in every case, but largely by looking at it and say if it is air being compressed or nitrogen being compressed at ambient conditions, we can write it, but we must say explicitly that under these conditions we can say that throughout the process from beginning to end, we can assume that these conditions are such that ideal gas assumption is okay. Once we do that, we have the luxury of using PV is equal to RT and going ahead with the solution. If the problem explicitly states that there is a vapor, the word vapor comes in, or the word wet comes in, then we got to be careful that we cannot make the ideal gas assumption. The moment we come across these words, we must go to property charts and tables and get data from there. So this is an important distinction one has to make. It's a decision that we have to take quickly on, because then we will know what numbers to put in the problem while solving this problem. An example of a wet system, there are some problems that we had given in the assignment, is that say we have a cylinder piston arrangement in which we have a piston sitting over there, say, and inside this there is a certain amount of liquid and certain amount of vapor over there, and we hit this against a certain pressure so that the piston rises to some other point. So we say this is state 1, this is state 2, and we want to know what happens during this process. So here we have to go for vapor properties. If the problem says that a gas is contained here, and if by intuition we know nitrogen or oxygen at about ambient conditions or higher temperatures, ideal gas assumption is really perfectly fine. But if the temperatures are close to the critical temperature or even lower than that, then we have to go to this route. Please keep that in mind. Okay, so that is the way we get the properties, and then we begin solving this problem and get whatever we want. Well, it always helps to show all these processes on some property diagram. For example, here I'm going to show this process on, say, a PV diagram. And so where is the initial state, and say if we take the example of, say, a steam engine. Now we do not see this, but 25 years back and the beginning of the Industrial Revolution, this was the machine that changed the world. So there the inlet state was here. This is the topmost position which the piston can take, which this is called the top dead center. The bottommost position it can take is the bottommost position there, which is the bottom dead center. For some time we admitted steam, then the steam valve closes. And then this follows a series of paths, series of states until the piston reaches the end, at which point the exhaust valve opens and the steam is let out, and it is now only got pressure, steam at the ambient pressure, slightly above ambient pressure. And then it comes back, and as it's coming back, it pushes that steam out. So these are the state it goes, but now it is an open system. This part was an open system because steam was coming in. This is a closed system. We can assume it to be reasonably like it is adiabatic, and this is the outlet. Once it comes to the top, again we start exposing it to the boiler, and it again generates this. So that's how the classical steam engine used to work. So this is open system, this is closed system, and unless it's explicitly stated that there is so much heat transfer taking place between the surroundings and the piston, we can assume that this type of a device will be adiabatic. Okay, so adiabatic means heat transfer is zero. So whenever we make an assumption, we should explicitly write that I am going to assume that in this problem nothing is said. I'll assume this is adiabatic, Q12 equal to 0, and then we go ahead. Because in the absence of anything else, there is no way we can calculate Q12. So we assume it to be 0 and proceed with the analysis. So this sets up the problem. Again, if nothing is mentioned, what type of process is there, then again we have an issue. So we need to again say that, okay, let's assume that is isentropic, and then get PV to the power k equal to constant, and then solve the problem from there. So there are many problems that you will come across where you have a cylinder piston arrangement like this happening. It could be that the gas is expanding, or it could be that the piston is doing work, and there could be various variants on this. For example, there could be a spring-loaded thing, or the heavy piston being put, all types of things could be there. Practical applications of this is a reciprocating device, and the most common thing is a positive displacement type of a compressor. And most refrigerators or window air conditioners would have reciprocating compressors where they compress the refrigerant and put it out. What happens? So what we had shown in the earlier picture here as this, if it were a reciprocating compressor, it would be doing slightly different things. So let me just explain how these reciprocating compressors work. So what we have done is, here's a device, and it has got two valves. One, and this is connected to the inlet, this is connected to the outlet. What this valve does is that when the pressure inside is less than the pressure here, this opens and allows the gas to flow in, or the vapor. So this is what will happen at some point. And what this valve does is that when the pressure here is more than the pressure here, it pushes the gas out. So there are two valves which do this job. So there is one process which could be the intake process, where the valve is opened up, and this happens when the piston is up here and begins to move down and comes to this point. And as it is doing so, if the valve were kept closed, this pressure would be less than the inlet pressure. But since there is a valve, that valve opens entirely because of the pressure difference between the two sides, and this thing moves in, and so the working substance fills up this space. So now the piston has reached its bottommost position, it cannot go any further down, and so what happens now is that this thing begins to move up. The electric motor is driving this. The moment it starts moving up, the pressure inside here becomes more than the pressure here. So this valve will now remain shut. And we'll have to now see what the outlet valve does. So this begins to move up, and as it moves up, the pressure keeps increasing. And at some point, this pressure is equal to the pressure here, and after that, a slight movement up here, the pressure here would be more than this pressure here, in which case this valve will open and some of this vapor will be pushed out. So this, it will keep doing it until it reaches its topmost position. So from here to here, it is an open system where it pushed it out. After it reaches the top, this pressure is equal to this pressure, this valve closes, this pressure is greater than the inlet pressure, this valve closes. Now you have a closed system over here. And then what happens? The piston now begins to move back, which was what I do first here. But in moving from this position, as it comes down to say some position over there, it is a closed system in which the pressure inside is decreasing. And it will decrease up to a point when it is equal to this pressure. After that, when the pressure here is less than this pressure, then from there till the bottom part, this much, it will suck in the fresh refrigerant. So there is a push, this travel when it takes in air, and this part when it pushes it out. So even though the total displacement is from top to bottom is this much, the actual amount of vapor that is taken in is less than this total volume, because there was some dead volume here already which was always going to be there, and only a certain volume is what went out. This is, so if you draw it on the pressure volume diagram, here is what we get. Now you can put PV, also capital. So at when the piston moves from top dead center to the bottom dead center, these are the two states. Here the pressure begins to decrease, and then it reaches a point and then it goes in. So this is when it takes in fresh gas. Then from here it begins to compress, it reaches the top pressure, and then from here this is the discharge, and this is intake. So this much of the total volume that we had, which was this much, only that much volume was actually taken in. And this ratio to this ratio is an important indicator of how this thing works, and that's how much got discharged there. So that's the type of thing it happens. These two processes I have shown dotted simply because they are both. This is the expansion process, this is the compression process. So both we will assume to be isentropic in the ideal case. If it is not isentropic, then because it is a vapor, we can say that PV to the power n is equal to constant, that n could be different from K. So we have this isentropic expansion, isentropic compression, followed by constant pressure discharge and constant pressure intake. So that's actually what happens in all these reciprocating compressors. In the case of liquids, this compression is not too much. The moment it reaches here and it starts to compress, the pressure inside becomes higher, this valve will open and it will start pushing it out. So a liquid, this much will get pushed out. In a vapor, less will get pushed out. So that's the great difference between these two devices, in vapor and the gas part, the liquid part. You do not see too many liquid type of compressors with reciprocating thing, but when you want extremely high pressures, say 200 bar, 400 bar, 1000 bar, then either it is this type of a device or what is called a vane compressor. I won't go into the details of this, but you can look up on the web and see the devices. Or gear pumps, they deliver very, very high pressures. Where would we need such high pressures? In hydraulic control systems, for example. In an aeroplane where the wings and the flaps are to be adjusted, that is done by giving force to a cylinder piston arrangement with a high pressure oil in it, and that oil pressure flow oil pressure is regulated by an electronic controller, which gets signals from its main flight computers. So that is one example of that. Another example where you have the liquid going in and out is what you may see all your bulldozers and excavators, where the bucket goes in, scoops it out. Inside that long cylindrical thing is basically a cylinder piston arrangement in which you are putting not gas but compressed oil into it, and that does all the work for us. So these are all analysis could be done from this type of a system. Okay, so that's the first device that we have looked at, and that is your positive displacement device. A few words about the other ones. Gears is basically like two gears in mesh, and what you have done is created a space so that this is a gear, and this is in mesh with another gear, and the space around this is very tightly controlled. There is a very small clearance between them. One of this is connected to the inlet, this is connected to the discharge, and what it does is it's trapped this fluid which was trapped here, it will be carried forward and physically pushed into this thing. So that's how you can have two gears in mesh doing the job of a compressor or the job of a pump. So these are the two external gears here. One could be one external gear, the other could be internal gear. The most common example of this is the lubricating oil pump in every internal combustion engine. You won't see any diesel engine or petrol engine anywhere which doesn't have at least one of this for lubricating oil, and possibly a second one for, in the case of definitely for diesel engines, for the feeding of diesel fuel up to the engine. So a typical engine will have two gear pumps, two positive displacement devices. Screw compressors, as I mentioned, are two screws in mesh, so the flow happens normal to the plane of the paper. Very difficult for me to show it here, but we can see some pictures of screws later on and see how two screws in mesh can be made to behave like a compressor. And these days, the reason for bringing up this discussion is that if you look at large compressors for central air conditioning devices, or things where you need very high pressures and in a very compact way, one is going for screw compressors very largely, and in some cases, even your domestic refrigerators or air conditioners will have a scroll compressor. The reason for doing this is that what I mentioned just about how this device works is that out of this much displacement volume, you are only taking in this much fresh substance, compressing it and throwing it out. The volumetric efficiency of these devices is very low. They are bulky, and screw compressors, pumps, or scroll compressors, they do this in much more higher efficiency. So that is the reason why they are used, and they have already become much more popular than reciprocating compressors. So that's the reason for bringing it up in this discussion. That one must know that yes, you go to buy a fridge or an air conditioner, will say that we have a scroll compressor in this air conditioner, which is more efficient than a reciprocating compressor. The geometry is a bit complicated. I suggest you only way to understand the geometry is, I made this a cartoon out here, but you actually have to look at the engineering drawing of these devices to understand what are the very fine points by which these devices are made. So we'll leave the first item there. The second item on our list, as far as the equipment goes, is the heat exchanger. The term heat exchanger basically denotes a device in which we have two fluids that don't mix. One is hot, one is cold, and the hot fluid transfers energy to the cold fluid. So this is a very quick, broad definition. What is a heat? Largely, you will see these devices being analyzed in a course in heat transfer, which is where you do the detailed engineering of what I did. That if I want to have 1 kilowatt heat exchange between this fluid and that fluid, how big a tube should I have? What should be its length? What should be the velocity? All those considerations will come out of the heat transfer course knowledge. The thermodynamics knowledge tells you that, look, this is how much is going to be your pressure and temperature, no matter what the mechanical design or the thermal design of the heat exchanger. The common symbol is shown here, where with that and a zigzag lines. These zigzag lines basically denote that the fluid is one fluid comes in here and goes out here, and in going so, it could be like this, that it comes in here, goes through many parallel tubes, or maybe some are in series, and then connect again and goes out. So that's a typical design of the radiator of an automobile. If you open up the hood of a car, or you look at any diesel generator set, your radiator will look like this. There's a bunch of tubes going vertically. You see a lot of fine sheet metal pieces there. That is the fins which came from the heat transfer considerations. And that whole device is basically that the hot water is flowing inside this, becoming cold, and outside this we are blowing the cold fluid, which in the case of a radiator is ambient air. So that air goes over it, and as long as the temperature of the coolant inside is more than the air temperature, it will give heat to the air, cool down, and the cold fluid will go out there. So that's a very common example of a heat exchanger. The difference is that we do not have this outside thing shown there, so we can just show like this. But if the fluid, so this fluid which goes in it, it's called the tube side fluid. It could be either the cold fluid or the hot fluid, that depends on the design. And the fluid which flows over it is generally known as the shell side fluid. The radiator does not have, and what the shell means is that you have enclosed the other fluid also in a device, say a tank or a big enclosure. So the other fluid flows inside this and comes out. The tube side fluid goes only inside through the tubes. So when you make this entire thing, this gets known as a shell and tube heat exchanger. And this is a very, very common device used in not just power plant but refineries, practically any industry where some heating or cooling has to take place. So this is a very common engineered. So this is what happens, and the question now we'll ask, and for that we have split this problem two ways. One is the hot fluid and the other is the cold fluid. Don't mix. So what we will do in one case is to apply the conservation laws only to the hot fluid as the system. Then we'll apply the conservation laws only to the cold fluid as the system. So when we say that I will look at first the tube side fluid, we will say that it includes all the fluid that is contained in the tube from the inlet state 1 to the outlet state 2. And so the space inside all of this is my system. So this is a tube system, and we are only going to be looking at this fluid. Once we do that, what we find that this is an open fluid coming in, going through this and exiting the system. Our system boundary ends at the outlet of this tube. The system boundary begins at the inlet of this tube. So this is an open system. So the tube side fluid is an open system. Once we do that, we now know the first next is what is the working substance that we have. Is it water, or is it a coolant, or is it some oil, whatever that may be. And then, so that tells us where to get the properties from. Once we know that this is an open system, we know that we have to write conservation of mass and then the conservation of energy, the first law, and the conservation of the entropy equation, the second law. And so this is what I need to solve. Then we make a set of assumptions which will be true for both. In this case, we will say that this is a flow type of a system which is open. We'll assume there is steady state. If nothing is mentioned, we will assume that. And we'll say that kinetic energy and potential energy changes of the fluid on the tube side is 0. So we put that there's only one inlet and one outlet in the system. So this equation will become m dot 1 is equal to m dot 2, and this equation will become, and say that the fluid going here, there is no work transfer on it. So w dot cv is equal to 0, and so we get the first law equation as m dot 1 h1 is related to m dot 2 h2 and q dot cv. And in this case, we can say this is q dot cv, tube side fluid. So everything is for the tube side. So this is one equation we have which tells us what is the relation between mass flow rate, inlet outlet enthalpies, and the heat transfer rate. Then depending on the substance that we had, if it was a vapor or a liquid, we deal it in one way. If it is a gas, it's something else. Even liquid, if we know throughout the system there is a liquid, like say water is going through it, Then in both cases we will write the difference of enthalpy as Cp or Cp0 minus T1 minus T2 or T2 minus T1, whichever way that is. So we only need the constant pressure specific heat of the material. If there is a phase change, we cannot do this. Then we have to go back to H1, H2 and get H1, H2 data from the pressure and temperature at the inlet and outlet. So in the example of an evaporator of an air conditioner, you would have, say, subcooled, you have a mixture of vapor and liquid going in, so it is wet, so you need the dryness fraction at this point along with temperature to get specific enthalpy, and this side could be superheated vapor, in which case you need pressure and temperature here. You go to the property charts for the working substance that we have put up here and get the data from there. Cp T1 minus T2 will be a round thing. So this is what we would do for the tube side, and we could do the same thing for the other side, which we can say the shell side. Exactly the same thing. We can say that the fluid and the system boundary is from here and includes everything and ends over here. So everything contained on the shell side of this, excluding all the metal, this is our system, and the working system substance in this case. So this is also an open system. There, the substance coming in and going out, the system boundary ends over there and there. Working substance could be whatever. If it is, say, a radiator or the evaporator, the working substance will be air. Or it could be water if it is a water device. And then we follow exactly the same process that we did here, get the properties, and in this case we will get Q dot Cv for the shell side. And the thing that joins and completes the problem is that these two terms have to be equal, that is heat given out by the hot fluid Q dot Cv is heat transferred to the cold fluid, and these two are equal. So something that we know from experience, that m dot Cp T1 minus T2 for one substance will be equal to m dot Cp T1 minus T2 for the other substance. That comes out from this derivation. We can then go about doing all the other analysis. The only thing to remember that for liquids and gases, Cp T1 minus T2 is fine. If there is a phase change, we have to worry about getting properties from the tables. So evaporator is the case where a subcooled or a wet game, a superheated state, is the same thing as that. Saturated state becomes a liquid state, and there are devices where you could take superheated vapor and cool it to a subcooled liquid. The next thing we'll do is show these processes on one of the property diagrams. And I'm choosing to show it on the TS diagram. So let's take the evaporator of an air conditioner. We know that there's a wet state, so the dome has to be shown on the TS diagram. If it were on the air side, we don't need to show it. So we will say this is the tube side, which is the refrigerant, whatever that may be, say R134A. And we'll make a TS diagram simultaneously for the outside fluid, which is the air. So in this case, what is happening is at the end of the condenser, we got slightly subcooled liquid, and this was throttled. Now, throttling is a highly irreversible process, so we don't know what states happen in between. But at the end, we know that this is enthalpy doesn't change, so it will follow a constant enthalpy line. The constant enthalpy lines on a TS diagram look like this. So the inlet state to the expansion valve was there, and the outlet state was there. In between, we do not know what happened. The one way to show it is that we put dotted or dashed lines along this line and say, look, it is irreversible. That's number one. That's why I'm not drawing a solid line. And second, I'm superposing it on the constant enthalpy line just to tell you that this is a constant enthalpy process. But otherwise, any other line being, because it is irreversible, is fine because the intermediate states are actually known. So this is the inlet state to the evaporator. From there, it goes off there, and then what has happened here is that this phase change is constant pressure. We cannot have phase change with increasing pressure or decreasing pressure. And in all heat transfer devices, this fluid that goes through the tube, we are not doing any pumping on it. So the best and the easiest assumption is that the process throughout on either shell side or throughout on the tube side is a constant pressure process. So in this case, it will follow the constant pressure line which is there. So it will follow this and say end up over there. So the process that happens in that evaporator is like this. And we assume that the process internally is reversible. That's why we are drawing this solid line. So this was the inlet state, this is the exit state, and that is the process on the evaporator. Now what will happen on the air side? Now air side, we know that the air was warmer than this fluid at all states. So if this was say minus 10 degrees Celsius, this was say minus 2 degrees Celsius, and the air which came in was say 28 degrees Celsius and left the device at say 16 degrees Celsius. So that much temperature difference was there between the hot and the cold fluid at all times. And we know that as the air goes through it, its temperature decreases. So it started off having a temperature over there, and pressure is again constant. So we have to take a constant pressure line on this. In this case, the constant pressure lines, they look like that on the TS diagram. The dome has not to be shown because this is not a vapor state. We are implicitly saying and assuming that air is an ideal gas. And for ideal gas, the dome is not to be shown, but we show the constant pressure lines and say now where is the inlet state? Let's say, okay, this was my pressure, this is the inlet state, this was the outlet state, and we say that this was the reversible heat transfer. So the air process was like this, the refrigerant process was like this. This gave away Q dot CV, and this took in all of that Q dot CV. Now I made two separate TS diagrams to clearly illustrate what was happening in both cases. And say, well, can I join these two diagrams to make one picture? The answer is yes, it is possible. The only issue is that temperature in both cases is the same scale. It's an absolute scale of temperature. So 0 for this is the same as the 0 for this. The trouble is on the entropy side. For R134A, there could be some temperature, say minus 40 degrees C, where HF or SF are taken to be 0. But for air, we could have taken some other temperature. If we reference both of these to the same value, say that look, for air also, I will say that H is equal to 0 at minus 40 degrees C, or I take both of them to 0 Kelvin and say S is equal to 0, then the two scales become exactly the same, and you can join all of them together and see what the composite diagram will look like. That will be the correct thing to do. If we do not put the scales on the S and T and match it, the diagrams will be there like you see in most books, that they have said that one process is like this in the dome and the other process is like this. But strictly speaking, the entropies here do not match. This could be here, this could be here, this could be there. It doesn't matter. Okay, so the main assumption that has come out of this is that in addition to all the assumptions that we do, heat transfer processes either through heating or through cooling, we take this to be isobaric processes. That's the additional thing that has come out. And the reason is that these are substances going through a device. We are neither doing work on them, we are neither doing great expansion on it, and so the pressure in the first analysis is assumed to be constant. In the real world, if we have a system like this, like the radiator or the evaporator or the condenser, as the fluid flows through these tubes, there will be a frictional pressure drop. The outlet pressure will be slightly less than the inlet pressure, and the real engineering will have to factor that in. The data on how much pressure fluid mechanics or heat transfer, and that can then be put back into thermodynamics and say that in this process, if there was a pressure drop taking place, what will be the state? It will be that as it keeps going, there is a slight pressure drop all the time, it comes over there, then it would have gone along this, but there is a pressure drop, so the lower pressure isobar is there. So from here it will go and finally end up at this place. So the real substance will go like that, and the pressure here will be less than the pressure here is less than this pressure. But in the analysis that we do, if that is not given, we assume it to be a constant pressure heat transfer process to the analysis. Okay, so that is the idea of a heat exchanger. Okay, one more type of a heat exchanger that we have not talked here. Let's take a little look at it, then we leave it. Is what is called a boiler. Very common device. That's your main thing that produces high pressure, high temperature steam for generating electricity. A boiler, I can even put it this as a nuclear reactor, or in these are even solar collectors. What happens here is that on the tube side, it is the same process that happens in the heat exchangers that we have seen. So you have tubes in which the fluid, cold fluid enters, gets heated up and comes out. But what's happening outside the tubes is that in the case of a boiler, we are burning a fuel. So there's a tube there into which we are putting the cold fluid, but outside here there is a flame or a fire or a combustion taking place, and this is transferring heat to the tube. This is not just by convection like we saw earlier, but both convection and radiation, it is heating it up. In the nuclear reactor, the heating takes place because you have a fuel rod in which heat is being generated, and outside this the coolant is going out, and this coolant gets hot and comes out. This could also result in phase change if it is a boiling water reactor, a BW water. And a solar collector, you could have a bunch of tubes in which this fluid is flowing, and they are just getting heated from the outside by solar radiation. So the outside is not strictly a heat transfer in the classical sense that we have seen, but at least on the tube side, our analysis will be exactly the same on what we have talked a few minutes back. So there's only a tube side fluid, and its analysis can be done the way we have looked at it. Okay, the next set of equipment that I used, I put three names here: a compressor, a fan, or a blower. There's slight difference between them, but what all of them do is they cause a gas, typically air, to flow. And in particular, we are looking at the fact that these are what are called centrifugal machines, as different from positive displacement devices. So the simplest example of a fan is your ceiling fan. So all you have is a hub with blades on it, and there's a motor inside this, so you give electricity to it, and it causes an airflow over there. So the same thing with more blades, like this exhaust fan of the kitchen or the bathroom, that would be a fan. A blower is slightly different. You would have seen a blower in some of the desert coolers, where there's a circular device into which air goes in, and on this there's a wheel with these type of things. This is rotated, and as the air comes in from this side, it throws it out on one side. That's one type of a blower. So what fans and blowers do is that the pressure increase in these devices is very, very small and very modest. It's not very large. Millimeters of water, tens of millimeters of water is all you get here. And we don't really need much more than that. So say a blower that is used in the air conditioning of a whole building will be one blower at one point, which is called the air handling unit, AHU. That takes in air, part of the air from the room itself, gets in some fresh air and blows it, and that goes over the evaporator coils, and that you get cool air inside the building. That's the AHU. Compressors, the difference is that delta P here is quite large and substantial. So here there is compression taking place. So density increases. Here density is almost constant. So we can treat this as incompressible flows. So we can treat that air density is not changing even though it is air and small changes in pressure are there. But here we cannot make that assumption. And the reason we say that density is constant is because delta P is very small. That's why we can say the constant density or incompressible flows, this would be treated as a compressible flow with pressure changes. In making schematic diagrams, we use three symbols over there. So this means that the gas or air goes in. Inside this, there is a shaft on which there are blades. The air keeps flowing over this, or the gas keeps flowing over this. There is a rotatory part which will give momentum to the gas, and a stationary part which will reduce the kinetic energy and increase the pressure without any work input or heat input. Then the next stage will do it a little more. So like that we do the compression. First we give momentum, so of the energy, and then we retard it. When you retard it, it's like a diffuser basically what we have, and because of this the pressure goes up. And then we can again put it into the next set of blades, do the same thing, and do the same thing here, then again. So this would be called multi-stage compressors, and all practical compressors by and large are multi-stage. The aircraft engine is a good example of that. In schematics, we can also use this symbol, largely for, sometimes for compressors, but largely for fans and blowers, these symbols. Okay, so now we said, how do I analyze these? And for that we accept that to do this happen, there has to be a work input in this. So we can show here by a symbol and write a motor, that is a motor powering this, or this has got a motor, this is powering this device. So what it does is you have work input taking place, and the system we first define in all of these. We say that look, I will take all this is my system, or one can say that this is the system excluding all the metal and only say the gas or the working substance which is there, air or whatever. So this system has one inflow, one outflow, and there is a power, shaft power being input to this. So once we have drawn the system boundary, we know that these are open systems. Even in this case, the story is the same. We can show the system boundary to be like that. These are open systems. That means we know that conservation of mass, conservation of energy, and entropy equations, which ones to put. And then we say that this could be air, or it could be some other gas that may be there. Say methane is a natural gas, Mg. And then we say, okay, if this was the working substance, now what are the equations we have to write? So that we do that. And the next step is what the assumptions. And that helps us to get that big equation into a simple thing. And the main assumptions we do here is firstly, of course, that being a flow system, we say this is steady state. Nothing changes with time. Then we say that delta PE is equal to 0 because the potential, the elevation difference between these devices, in some cases it is negligible, in some cases it may be a meter or two, and meter or two rho GH is negligible compared to the other changes that take place here. So delta PE equal to 0 is justified here. Unless otherwise given, delta change in kinetic energy can be assumed to be 0 if there is no mention about velocity in the problem. However, if the velocity typically either at the inlet or at the outlet or in both places is specified, then this is not to be assumed. Then the velocity term will remain in the first law equation. Okay, so if V1 or V2 or both, they are given, then this is not the case. Okay, so then this will be wrong. So once we do that, we get to the equations, and then we are in a position to solve. Now, this type of device and this is where engineering comes in, they always handle a single phase flow. Even the earlier device, which are the positive displacement devices that I mentioned, they also are designed for handling single phase flow. The practical engineering of these machines, if you had a wet substance going into this, is extremely difficult, in large part because liquid will accumulate here or there by gravity, or liquid droplets will go and hit the moving parts and break it up. And so we always make it a point that no matter what type of a work transfer device it may be, whether it is a positive displacement, compressor, fan, blower, these always handle single flow. So these devices or that other earlier device, I said they will be either handling a vapor or a gas. I am not putting the word liquid over here because that we will see in a minute. That machine that handles liquid is not called compressor, fan or blower, but it is called a pump. So we'll look at pumps separately. Okay, so this is very, very important. The moment we say it is vapor or a gas, if it is a vapor state, it will be superheated vapor. It cannot be a wet state. And it could be possible to assume ideal gas behavior, but if it is like nitrogen or oxygen, in that case, ideal gas behavior is okay. Otherwise, like in a refrigeration system, we will have to go to the property tables and get the data from there. Nevertheless, this process can be approximated by something like PV to the power n equal to constant. If it is PV to the power k equal to constant, we also know additionally that this is a reversible isentropic process and I can use this equation in Y. But the important part is that compressor, fans and blowers, they handle a gas or a vapor, and they never handle either a liquid, and of course no machine will handle a wet substance. And we'll see that in a minute on what it means for the implication in designing cycles. But the wet state inside a work producing device or a work consuming device is a big, big problem. So all engineers will do everything to avoid that. Okay, so that's the assumptions, these are the equations. Then we get the conservation equations that m dot 1 equal to m dot 2. We put the states 1 and 2 or inlet and outlet, and then get what will be the work transfer W dot CV in this case in terms of properties. On the property diagrams, say we take the TS diagram. If it is a vapor, we will have to show the dome, and compression will be from say this state to this state. This is what happens in a air conditioner or in a refrigerator. So we are well below the critical point. We are not very far away from the dome, so we will show the dome that this is the compression process. On the pH diagram, again we will show the dome, and we say, well, what are the constant entropy lines? Here we have assumed it to be isentropic. These are constant entropy lines. I say, well, what is the constant entropy line? This is the constant entropy line. Where are my states? I say, okay, your inlet state is there, your outlet state is there. This is the compression process. And now we say, well, what if the process is not isentropic? Okay. But being small devices, and we do not want to make life too complicated, we not only say that this is the case, we also say these are all adiabatic. So the important things about work consuming, work producing devices is firstly they are adiabatic, and from an engineering context, we necessarily have a single phase in it. Now, if it were not a reversible process, and we say it goes to the same final pressure, so in this case, the constant pressure lines are here and here. So the inlet pressure is assumed to be constant. The discharge pressure is also the same. So this was P1, this was P2, and then an isentropic compressor would do that. So this we will denote as 1 to 2. S means isentropic, and 1 to 2, this is the real case. A dotted line because the process is irreversible. So if you have to calculate the real work from the isentropic efficiency, or if you have to calculate isentropic efficiency, we need to know one of these things. Either this change, P change, or the work input. And two of these are known, the third one can be calculated. On the pH diagram, the discharge pressure is going to be the same, inlet pressure is the same, but entropy has to increase. So these are the lines of increasing entropy. So this will go off on that side. So if nothing is said, we say that isentropic efficiency is equal to 1. If it is the value is given, then we know that we need to calculate one of these 2 points from the isentropic efficiency. So those are the important things about fans, compressors and blowers, that we take that these are adiabatic. They will handle a single phase substance. This is not that thermodynamics says you cannot handle it. Thermodynamics says yes, you can put a wet thing through it. No, the science is not wrong. The engineering says that look, it's too much of a nuisance. Equipment becomes unreliable. We will not make equipment, and nobody makes equipment like that. And unless specified, we assume isentropic efficiency to be 1. If it is not 1, we have to take that into the problem and then begin to solve it. So now we come to the counterpart of the compressors and fans, and we say, well, we now look at a centrifugal pump. The word pump means that this handles a liquid. But what we know from thermodynamics is that what we call in common language as liquid is, we can call it either a subcooled liquid or a compressed liquid. And in all cases, we assume that this is the symbol for that, a circle with an arrow. And we say that this is the inlet and this is the outlet. Inlet state is 1, outlet state is 2. Throughout the state, the process, it remains a liquid. We do not want a situation whether either the inlet is wet and then you make it into a compressed liquid. That's not something we can do. But like I said, the earlier principle about engineering is that this will be single phase. But there is one condition where we do have a problem. It's a practical problem whose roots lie in thermodynamics. We will see that in a few minutes. So what does a centrifugal pump do? Firstly, it's a liquid thing. The moment we say this is so let's go the systematic way that we would like to approach this. Having made the symbol, we say that this is our system boundary. And so, well, there is one inflow, one outflow, and to run the pump, we have an external prime mover. This could be a motor or a diesel engine, like you see in agricultural applications. So there is work input to the pump. We have one inflow and one outflow, and we say that our system is everything inside this, but that's only the working substance there. No metal, oil, anything else is considered. This system we know is an open system, so there is one inflow, one outflow. And we know that this is a liquid, so let's say, well, how can we then begin the analysis? First thing we assume is steady state. So when I'm writing this, we actually should be saying that this is assume that there is steady state, and elevation references are very small. Delta Ke equal to 0 is okay. And pumps, even though they increase the pressure, they don't increase the velocity very significantly at all. So it is perfectly fine to say that, the kinetic earlier case, elevation was 0, so delta PE is equal to 0. Since velocity changes in the machine are very small, we can say the kinetic energy change from inlet to outlet of a pump is also 0. So with that, we know now that it's open system. What are the conservation equations we have to write? Then under these assumptions, what do the equations become? And in this case, conservation of mass becomes m dot 1 equal to m dot 2. And then we also say that this device does not lose heat if it is a hot substance in ambient or it is not being heated. So we'll say that this is an adiabatic device. We said the same thing about the reciprocating machines. We said the same thing about compressors and blowers. Here also we say adiabatic means that Q dot CV is equal to 0. So all we get is m dot 1 H1 is somehow related to m dot 2 H2 and plus Q dot CV. So we can write that equation. So although we had a very long equation to begin with, under these assumptions, the equations become very simple. And after some practice, you can directly jump to this. If you are certain that all the assumptions are there and you are aware what the assumptions are, and you must write what those assumptions really are. So that's what happens. That's the equation, and then we can, sorry, not W dot C, this is W dot C, the work. So we can calculate the work. The difference between the treatment of pumps and the earlier type of machine is that here we have a liquid. We have argued some property considerations earlier that for a liquid, V is like constant. We say that liquid and solid are incompressible. That's the thing that we are saying, that V is constant. In which case, we know that H1 minus H2 is V P1 minus V. We assume V to be constant, and the question is which V to take. Should V be at state 1 or V at state 2? Either value would be okay because the difference between the two is very, very small. But if someone wants to be very, very clear and very precise, you can say that I will take V as the average of V1 and V2. But that really is not going to change the result very significantly because the change is hardly 0.01%, that type of a difference. So you can take either V1 or V2, but explicitly mentioned there in the solution that since the liquid is incompressible, we are taking specific volume of the liquid to be specific volume at state 2, whatever the pressure and temperature may be, or at state 1, if you know the pressure and temperature over there. So this is the thing we are bringing in here. In the case of fans and blowers also, where we said air is incompressible, there also approximately we can put this, otherwise we can always go in gases as Cp0 T2 minus T1 and work out from there. That's fine. But liquids, this is the important difference. And now let's see how do we show the process on property diagrams. Okay, this is TS, and one thing we need to know, okay, we need to here of course mention somewhere or check somewhere that this is valid in the given problem. Fortunately, what happens is when you compress it, it becomes more of a compressed substance. So as long as the inlet state is a compressed liquid, or in some cases a saturated liquid, the moment you compress it, it will become a compressed liquid. So if the inlet state is a compressed liquid, then we are safe that throughout it will be a compressed liquid and our assumptions are fine. That's something to check. Okay, now let's look at TS diagram. I said we are pumping water at ambient conditions, and we know that ambient water is slightly compressed liquid, and when we compress it, the pressure goes up, and in the ideal case it is adiabatic, and if it were reversible it will go up over there, and this will be 1 to 2. I am exaggerating this because as I showed you the TS diagram, the lines of 500 or 50 megapascal is pretty much very close to this, and so if I actually have to show this diagram, we can't even show it. simply because the effect of pressure on properties is so very small. But here we have done some exaggeration and showed it to clarify that inlet state is compressed liquid. This is isentropic compression in the ideal case. It has gone from there to there. The real compression will go to the same pressure. Isobars are like that. So the discharge valve pressure isobar goes somewhere there, but is extremely close to this line, so it's very difficult to differentiate that. This is the isentropic case. This is the real case. If you are saying that we take saturated liquid and then we compress it, and that's what happens in a power plant thing, where we have condensed the water into a saturated liquid and then we start pumping it. So we can say that the initial state was here and then we started pumping it and it went there. So it started one as a saturated liquid, went here, and in the ideal case it went slightly over there. Okay, so that's the pumping of a saturated liquid. In the practical world, this is a very tricky operation. So pumping saturated liquid, where do we encounter it? I've given the example of every power plant condenser or condensate pump. Also the main boiler feed pump. Again, we are trying to compress a pump, saturated liquid, and cryogenic engines. ISRO is launching rockets very frequently these days, and they all have a cryogenic engine where you have a tank containing saturated liquid oxygen. So there we can say that here's a tank, LO2, or there's another tank, liquid hydrogen. Both are saturated liquids at 1 bar pressure. And we take a pipe and we put it into a compressor that goes into the combustor. So here is the problem that happens with saturated liquid, that saturated liquid is a static case, but if I have a condition where it begins to move in a pipe, then because its velocity is increased, and what we have learned from thermodynamics is that here and here, if I apply the first law, here velocity is 0, here velocity is finite. So this was state 1, this is state 2. All the assumptions of steady state flow we take, then H1 is equal to H2 plus V2 square by 2. And even if V2 is very small, it tells you that H2 is less than H1 and pressure P2 is slightly less than P1. That means the moment you take this state and try to pump it, it will go there, which means that some of the liquid became vapor and you ended up with a two-phase mixture, and that's the problem. Vapors, as you have seen, the specific volume is very large, suddenly the whole thing becomes crazy and the engineering becomes very difficult. And so we have to ensure that we give at least minimum some static head, so that this is saturated liquid, but as it goes down, the gravity head rho g h adds on to it, so the pressure here under no flow will be more than the pressure here, so it will be slightly subcooled, slightly compressed liquid. Then as you pump it to the pipe up to the inlet of the pump, the pressure drop will take place, but at no place do we ensure that pressure is less than P sat at the given temperature. This is a very important consideration in designing all these type of devices. So even in a pump like this, where it is taking compressed liquid and you have an impeller that is rotating very fast, very close to the surface of the impeller, the velocity is very high, in which case locally the pressure at that point will be less than the saturation pressure at that point, and you could have a vapor bubble being formed. The moment this vapor bubble moves out into a zone where the pressure is more, it will compress suddenly and it gives out a shock wave, and that's why you will see that some pumps sometimes make a hammering sound, that there's something is being hit inside it. There's nothing hitting it, just that this device is happening, that vapor is being formed, and this is called the issue of cavitation. Even in the propellers of ships, especially naval ships, where the propeller is rotating in water, the surface, the velocity of the water adjacent to the surface of the propeller is high, its pressure will be less, and if the pressure becomes less than the saturation pressure at the ambient temperature of the water, it will become a vapor bubble, it will move out, collapse, leave a pressure wave, and that becomes a signature of that device, and somebody else can detect your ship. So it's a big challenge that you want to control cavitation in that case for defense purposes, but in our cases here, because when these bubbles form and break, they send out pressure waves and they do mechanical damage very badly, and in no time at all, the machine can get destroyed. So we would like to take care of that. But this is why the thermodynamics tells you that an important thing like cavitation actually happens, and what we need to do is what engineering is all about. Okay, so pumps will always start in the either in the saturated liquid state and go up, or in the compressed liquid state and go up, but never in the wet region. Again, we handle only a single phase. Okay, so this is about pumps. In a nuclear power plant, substance is steam, and this, of course, we assume it to be an ideal gas. These steam turbines are used largely for power generation, and also in the case of ships and submarines for propulsion. Nuclear submarine or a nuclear aircraft carrier, it has a nuclear reactor which produces steam. That steam runs a steam turbine, which produces some electricity. But gas turbines also use stationary applications like power generations. Gas turbines are also used for propelling naval ships. Not so for say cars. Traditionally, we do not look at in a thermodynamics course. The working substance is water and different from steam. We met this is water that's there in a river or in a dam. This gives you the idea of a hydro turbine. And the equation you use there, although they came from fluid mechanics, the basic idea was that it did satisfy the laws of thermodynamics. We call hydro turbines, and they are used for producing electric power, and in some cases running mills and turbines. So the working substance, if it is steam, we have to take it as from the property tables data. Air, we assume it to be an ideal gas. Hydro, we assume it to be a compressed liquid. And here we have to worry about what I mentioned in the case of pumps. You have to take care of cavitation. So that's one thing to worry about. Give some idea of what are the sizes of machines. The biggest turbines that are there are steam turbines, which have gone in power up to 1,300 megawatts. And then all the power generation devices. And there are smaller machines. A propulsion turbine could be like 3 megawatts to 5 megawatts. Gas turbines, the biggest stationary gas turbines are of the order of 130, 140, 160 megawatts. Aviation turbines, we don't talk of power, but we look at what sort of a thrust they can make. Tank converters, these are about 1 to 2 megawatts. We'll draw that on. So, what are the assumptions we have seen there? What equations we have that we have looked at? We assume that if there is no other information given about this thing, we say that this is adiabatic. If it is specifically mentioned that it loses some heat, some Q dot Cv is there, then we take that value in the first law equation. Otherwise, if there is no mention, we can assume that the turbine is adiabatic. Now we see what it looks like on the property diagram. It's a TS diagram. And if you are looking at steam turbines, we have to show the dome. And in this case, as I mentioned in the what you would like to do is avoid a two-phase mixture inside of machine like a turbine. So in power stations, we start off with superheated steam, say there, expand it up to this point in one turbine, and then we take the steam out, send it back to the boiler for heating it again, and then bring it back almost at the constant pressure to the same temperature, and then we start expanding it in not just one turbine but multiple turbines until it gets the temperature that is there for us, 45 degrees Celsius or so, slightly wet steam in the end of the turbine. That's where we have to be careful about the engineering of it. So that's what power steam turbines would do. Nuclear turbines would have pressure somewhere, say over there. They produce dry saturated vapor from a nuclear reactor, and this is expanded. And as you keep expanding, the quality keeps going down, so that engineering keeps getting complicated. So we say that, okay, I will come to a point where X is of the order of say 0.8 or 0.85, and then I cannot tolerate too much of liquid in the turbine. It will break my turbine. So what we will do is we will take this steam out and physically separate the liquid from the vapor, because there is a big density difference. So the vapor state, when it is separated from here, will come over here. The liquid state from here will come over there, and then we put it into another turbine and expand it until the cooling temperature is there. So this is a physical separation device. We will look at this later on in case when you look at another type of an application. But that's what happens in nuclear turbines, and including nuclear turbines on ships and submarines. You are always dealing with a wet substance, and you have to always be very, very wary about it. Okay, so that is it. And then what about gas turbines? So gas turbines, we do not show the dome. We assume that we are far away from this dome, way at the top, somewhere over there, much beyond this. So when we make a gas turbine diagram, we'll put this as T and S. We won't show the dome at all, and we say that the gas turbine expansion is from say there to there in the ideal case, and in all cases, if it is an isentropic turbine, the specific entropy will increase, but the discharge pressure remains the same, just like this. In this case, the constant pressure lines are like that. So this is P1, P2, and the anisentropic turbine, in this case, it will start from here, but it will end up over there. This is 2S, this is 2, this is 1, this is 2S, this is 2, and in this case, the throttling, if it is an isentropic turbine, the quality will slightly improve. So here is one practical advantage we get of throttling, or say friction, or irreversibility, but it works to our advantage as far as an engineer is concerned. Thermodynamically, it goes against us. Okay, so these are the type of turbines that are there. If it's a hydro turbine, well, on the same diagram, it will be completely on this side, but it will be too small. So if we blow it up and we say that, forget about that, we are only looking at compressed liquid, S and T, then the hydro turbine will be like this. Okay, so that's how we show the processes for the steam turbine, all types of turbines. These happen to be exceptionally sophisticated machines. They are rotating with very fine clearances, and these temperatures, as I mentioned, we are continuously trying to increase this temperature to get better and better thermal efficiency. So that's about the turbine. Now let's take a few questions that are there, and then we'll continue.
Morning, sir. My name is Sarabjit Singh, and I want to ask a question. That's what is the difference between classical and statistical thermodynamics?
Okay, so we'll take that up. Okay, so the question is, what is the difference between classical thermodynamics and statistical thermodynamics? We start from two very basic, different concepts here, but at some point, under some assumptions, statistical thermodynamics becomes classical. In statistical thermodynamics, we look at every atom or every molecule and assign some properties to it, irrespective of the phase. Most notably, if it is in the gas phase, then we apply the kinetic theory of gases. We assign some properties to every molecule, and then we look at the statistical average, because there are too many of these molecules, we cannot talk about each and every one of them. So we look at the statistical average and start developing theory from that point. So we look at all molecules, take a very large ensemble and say, now what does the average look like, and from there what do I get in terms of pressure, in terms of energy, in terms of various other things that we know. In classical thermodynamics, we say, well, we are not going to look at each and every molecule. We will say, we will make the assumption that we are looking at a continuum, which means that the smallest element of the substance that we consider, and this one can approximate this, say, as the cube, has got enough molecules or atoms in it that the statistical average of this is good enough to tell what the entire element is all about. So whether it is pressure, temperature, enthalpy, all of that we can get by looking at sort of an average of all of these, and we will not worry about where that average came from, but we start off by saying that this is the smallest element we have, some size we can put on it, this is of the order of angstroms, a fraction of an angstrom, this is much bigger, 100 times bigger than this intermolecular distance, and so we take all of these in an element, take the average properties of this, and start talking about all the laws and everything else that we have learned in this course. So whether it is talking of specific volume, specific U, H, S, or any G and A and all those properties, including pressure and temperature, we are assuming that it is a minimum size of an element is this much, and only because of that we are able to assign properties to that. We cannot assign individual properties to each and every molecule and hope to track every one of them in a problem. So that's the difference between statistical and continuum mechanics. Some aspects of this can come from knowledge of statistical mechanics, but not the opposite. So that's the difference between classical thermodynamics and statistical thermodynamics. If you want to look at things like reactions and mixtures in a very fundamental sense, one has to go to statistical thermodynamics, and that's not the subject of undergraduate thermodynamics courses. We do that typically at postgraduate level and at research levels. So there you have to learn statistical thermodynamics. Okay?
Thank you, sir.
Good morning, sir.
Good morning. Yeah.
Question is, what is the difference between mechanical and thermodynamic work?
Mechanical and
Thermodynamic work, and which devices are used for, means in which devices mechanical work takes place and thermodynamic work takes place.
Okay, so simply, if we look at what we have learned in this course, right in the beginning, we defined what was thermodynamic work. That when a force causes a displacement of a system boundary, this we said is work. And we said this is thermodynamic definition of work. Now this includes everything. It includes a mass being pushed and taken through a distance, or a shaft turning around and giving a torque at a certain speed and doing work on something. So this could, all of that would be then classified as what you have called as mechanical work. But this includes electrical work. That means current flowing through a device, a conductor or a heater. When the current flows through it, there is work inflow into that system. So current is because you have a charge going across a field. We could have magnetic work, a magnetic dipole going in a field, or we could even have like the cylinder piston arrangement. There's gas pushing against the piston and doing work. Yes, push, that we would call it mechanical work. Or say the pulling of a wire, or increasing the surface area of a device, say surface tension working to produce work. So strictly, if you look at mechanical work, we have called F dot ds primarily as force on a rigid body causing a displacement. That you may say that is mechanical work. But thermodynamic definition of work includes everything that includes F dot ds. So charge moving in electric field in a fuel cell or in a battery is still work. but we do not call it mechanical work. So this is a much broader, over-encompassing definition of all types of things where F dot ds takes place. Mechanical work we look at largely only as a rigid body being acted upon and a displacement taking place. Okay, so that is the difference. So mechanical work is a subset of thermodynamic work. Yes?
Good morning, sir. And I have the doubt that in a refrigerant R134A, what does 134 signifies?
Okay. The question is, in many problems I put down refrigerant is R134A. What is the meaning of 134A? So very quickly to tell you a history of these things, it started off with various refrigerants like R12, which is now banned. This is CCl2F2. Then you got R22, there is something else. So there's a formula by which we convert this molecular structure into this part. So from there, you can look up web or literature anywhere and you can figure out what is the molecular structure of R134A or R410A or things like that. Okay, 410 and 5 series like R500 or R502, these are slightly different from these because all of these are pure substances, whereas these are mixtures for which we have chosen two different molecules, mixed them in a certain way that their property is sort of a pure substance. So that's what it is. I don't, in the notes I put down there, this I don't remember the exact formula of this, CCl, CF2 or something like that. But there is a very small method by which you develop these numbers. You can look up on the web or a book. I don't remember it exactly.
Thank you, sir. Morning.
Yeah.
Morning.
Yes.
Arun Thakra. My question is, what is the criteria to select any refrigerant or coolant for a...
Yes, sir. Go ahead. Okay, so the question is, what is the criteria?
What is the criteria to select a coolant or refrigerant for a system?
Okay. Okay, I'll slightly broad base this question. It's a very important and a fundamental question. So what is the criteria for selecting any working substance? For a cycle or a system or a process. So what happens is, let's take the case of refrigerants. In the case of power plants, almost always we use only water. And a reason for using water is, firstly, it is abundantly available. Second, its properties are such that they are reasonably good for doing the engineering of it. And the trouble is, if I can use water in a power plant, why can't I use water in an air conditioner? And this is an issue that will show you why majority of the air conditioners that you see do not have water as the working substance in an air conditioner. There are some air conditioners where water is the working substance. And if you want to see the exact numbers that are coming out of this, I suggest you look up the module 3 assignment. I think it's the last or the second last question, I don't remember which one, where I've posed exactly the same question, that I want a certain heat transfer rate and I have a refrigerant which is say R134A or refrigerant like R22 or refrigerant like water. Now problem with water as a refrigerant is that you cannot go below 0 degrees Celsius. So you cannot use it in a refrigerator to get minus 10 degrees Celsius and keep ice cream. Whereas all the other materials are good, so they can do the job. So water for a freezer, not possible. For air conditioning, where you want temperatures like 10, 12, 15, 16 degrees Celsius, water can be used, it is used. The trouble is that there are many criteria which go in deciding how do you select these things. Besides, the first comes, of course, the thermodynamic criteria. So if you look at the thermodynamics of these and say, well, what is the cycle in which I will operate? And you say that here is my TS diagram, and I am going to operate it between these two temperatures. So for some substance, this could be the saturation dome. For some substance, this could be the saturation dome. Some substance, this could be the saturation dome. So what happens is that in this case, you will never get a condensation if I have used this with this condition. These two conditions, this and this, are both okay. So in this case, what will happen is that the cycle will become like that. Your condensation will be there, and then the throttling will happen over there to this temperature, then there, and then it goes over there. In this case, it will be something like that, but here it will come over there, like this, and like that. Sorry, here. Now what is happening is, you look at these two states, and so first of all, my cooling rate will be m dot into the change in the specific enthalpy, say H1 minus H2 or whatever that may be. Now, do I get a sufficiently large delta H from this state to this state? And if you see that problem in the assignment, you'll find that for some refrigerants this value is a few hundreds. For water, this value is a couple of thousand. So you'll say, good, great. For water, this is very big, so I need a very small flow rate. Water is a nice refrigerant. But you look at the other properties now. So you ask that, this is my first part, how big will be my equipment, and say, well, what is the specific volume at these two states? This is 1, this is 2, and you go back and pull out V1 and V2. And you will see that for water at 6 degrees Celsius or 5 degrees Celsius, dry saturated vapor here, V2 is huge. That means the specific volume has become so big that I need a very, very big pipe to make this thing flow, and that becomes impractical. Unless we are able to control it and redesign the machine to take care of that, then we can do it. So we say, well, water is not very good. Then coming to all the other substances which are possible, we said that we were all these CCl2F2, CClHF2, all these type of families are there. But why did they come about? Because the properties of C3H8, C4H10, these are also very suitable as refrigerants. And initially, when ozone layer depletion came as a problem, you had to replace R12, and some of the things that were talked of was propane, butane, or mixtures of propane and butane. Well, the first criteria would be that, is it safe? Safe for the machine, that means you should not react with the machine or the oil, and safe for humans. What if it leaks out? And the nice thing about all these halons was that they were non-toxic. They did not react with the oil, they did not react with the components, the materials from which you made the component, aluminium, brass, or copper, or all those things. And so they became very, very popular, and they had very nice thermodynamic properties. The specific volume increase was also not very large. So they were great chemicals of the Industrial Revolution. But in 20 years, we saw that they were causing ozone layer depletion, and now we had to throw them out. So we started looking at different things which have less of chlorine, maybe less of fluorine, and start coming to other substances. But then these would also be okay. So, but then these are not very safe. They are combustible. If they leak out, you could have a possibility of an explosion. Inside the system where there only this substance, there is no way that there will be an explosion. Specific volume is one consideration. Then you look at the pressures that you get, the pressure here and the pressure here. For water, if I would 5 kPa there and say 80 kPa over 80 degrees C here and 5 degrees C here, the pressure here is very, very small. So this pressure, P1, P2, they are very much less than ambient pressure. But this is of the order of, I think, 3 kPa at 5 degrees Celsius. Ambient pressure is 100 kPa. What it means is that your entire piping and all the joints that you make, connections that you make with the pipes, they have to be very, very good. Otherwise, air will leak into the system. The moment air leaks into the system, the performance deteriorates very rapidly, and you have a big problem. So you like that the pressure should be just above atmosphere, so that air doesn't get into the device. So that's another criteria, that the pressure at this should be not just about atmospheric pressure, and this should not be very, very high. Not 60, 80, 100 bar, maybe 20 bar, 50 bar, 30 bar, something like that. So that's the second criteria. Specific volume was another criteria. Then we look at heat transfer rate, safety, and then, of course, as an engineer, you always have to worry about cost and availability. And these days, like it started off this whole thing, environmental impact. So these are many issues that decide which substance to use in the refrigerant cycle. But the starting point is that you say, well, does the thermodynamics make sense? The thermodynamics makes sense and the engineering is doable, then that becomes the candidate material for the next step of consideration. Okay. If the thermodynamics doesn't make sense, then we are in trouble. Might as well forget that material and go to something else. So before I leave this, let me tell you that water is used as a working substance in a refrigeration machine called a vapor absorption refrigeration system or vapor absorption machine, VAM. We cannot make very small window AC type of things with VAM, but large things like 60 tons refrigeration or bigger 300 type, they are very much there. And if you have waste heat source, they are very, very good options because their electric power consumption is 1/10 or 1/20th the power consumption of a vapor compression system. So energy efficiency wise, carbon footprint wise, these are great stuff. But the engineering is not at all easy in this case. We do not use conventional cycles. We take water and then we dissolve it in a salt and then we pump the salt, so the work produced for required for pumping is very small, and then we heat it to get the high pressure vapor back, condense it and use it for the refrigerant. So do keep in mind, look up the website and see vapor absorption machines. There are 3-4 Indian companies that make it. They are used in many places and they are a very attractive option because they are very, very energy efficient. Okay, so we'll conclude here and we have some more devices to look at. We will do them tomorrow. I'll solve a few problems, then we will go and we'll spend some time looking at vapor power cycles, the engine cycles, and see how to do the analysis of that. So with that, we'll stop here.